Welcome to class number 12 of transport phenomena in mesoscopic and nanoscopic systems. So last day we were discussing the reciprocal vectors and reciprocal lattice of graphene, and we found out that the two main reciprocal vectors that constitute the Brougham zone of graphene consist of these two vectors basically, and I also stressed on the fact that the reciprocal lattice of graphene is also hexagonal. Okay, so it is actually not difficult to prove that this is hexagonal. Just do it yourself. So in case you don't remember how to find the Brougham zone, let me discuss it briefly. So we have these two reciprocal lattice vectors, and corresponding to this we get reciprocal lattice point. So if this point is the origin, then this is one reciprocal lattice vector which I have drawn. This is B1, and this is basically our B2 over here, and then we have minus B1. So this is basically minus B1, and then this is minus B2, and then we have this vector which is B1 plus B2, and then we have this reciprocal lattice vector which is minus B1 plus B2. So we have 6 neighboring points. There are other points as well. For example, somewhere here there is 2B1, and then there might be B1 plus 2B2, 2B1 plus B2, all these points, but we don't need to go into all these points, okay, because what we have to do now is that we have to bisect these reciprocal lattice vectors. Okay, so the perpendicular bisector of this reciprocal vector B1 over here is basically given by this line. Let me use a different color. Is basically given by this line over here. This is a perpendicular bisector of the reciprocal lattice vector B1. Then the perpendicular bisector of this reciprocal lattice vector B1 plus B2 is basically given by this line. The perpendicular bisector of B2 is given by this line. The perpendicular bisector of this minus B1 is basically given by this line. Then the perpendicular bisector of this reciprocal lattice vector is given by this line here, and then for minus B2 the perpendicular bisector is given by this line, and the region enclosed by all this perpendicular bisector constitute the first Brougham zone. So this is our first Brougham zone, which was already shown in grayscale in this figure, and this region over here, these regions over here, these are basically parts of the second Brougham zone, and then there is a third Brougham zone, fourth Brougham zone, and so on. And this first Brougham zone is what is important, because all the properties are basically repeated. Okay, so the properties of the first Brougham zone, for example, the charge density, the wave function, everything is basically repeated in the second Brougham zone, and then in the third Brougham zone, the fourth Brougham zone. So there is no new information that the second, third, or fourth Brougham zone basically gives us. Whatever information is there in the first Brougham zone is also there in the second Brougham zone, third Brougham zone, and fourth Brougham zone. Okay, so so actually you might think that this spelling is Brillouin zone, and but the actual spelling is Brougham, and it differs from people to people how they spell it. So most of the people spell it as Brillouin zone, but the actual way it is said is basically Brougham. Okay. Anyway, so this picture here shows the Brougham zone of graphene in the kx ky plane. So this horizontal axis here is kx and vertical axis is ky, and it is not actually difficult to find out these points of intersection over here. It just you need to depend on geometry, so it's clumsy, so I would not be doing it here. If you are interested, please do it yourself. Now first let us discuss about the band structure or the energy and k vector relationship for graphene. We will not again go into the detail because the purpose is not a discussion of graphene, but the purpose is basically to elucidate the procedure that how you basically do it. And we have already seen that the energy, the eigenenergy, can actually be given by this equation E phi 0 equals to hk phi 0, where hk is a matrix. And now we already discussed that the unit cell in graphene consists of two atoms. This is the unit cell, this is another unit cell. So we have one atom here, we have one atom here, and so on. So the unit cell of graphene consists of two atoms, and so its basis basically consists of two components. So phi 0 is basically, I repeat again, it is basically a 2 cross 1 vector. Okay, and hk is basically given by summation over m hnm e to the power I k dot dm minus dn, where dm is the vector corresponding to the mth unit cell and dn is the vector corresponding to the nth unit cell. Okay, and hnm, again this is nothing but m. Okay, again I just repeat that we are here taking the wave function basis to be the space basis. Okay, so m is the wave function at the mth unit cell and this n here is the wave function at the nth unit cell. Okay, so now what is this hk over here? So let us write it down. So let us see this graphene layer. So let us take this unit cell over here, and as I stated that we are considering the next nearest neighbor because most of the contribution comes from the next nearest neighbor. For example, an electron cannot jump directly from this point over here to this point over here. It's difficult for the electron to directly jump. I mean, it's not that electron cannot jump from here to here, but it's very difficult. Okay, the probability is very low. Rather, it is actually easier for the electron to jump from here to here and then from here to here. So that is why, because this is a stepwise process, because the electron, any electron here may move to its nearest neighbor, for example here, or for example here, or for example here. We would basically be considering the nearest neighbors of any atom, okay, in the tight binding model. So now which atoms are the nearest to this atom? So remember that in the unit cell we have actually divided our unit cell basically consists of two atoms, and let us call it position A over here and let us call it position B. This position we call it position B. Okay, and when we write phi 0, this is a 2 cross 1 vector, so phi 0 we actually write it as psi A and psi B at any given unit cell. Okay, this is the wave function of the of atom A and this is the wave function of atom B. Okay, now note that if we consider this unit cell over here, so this atom A is basically, what are the next nearest neighbor to this atom? The nearest neighbors are basically this atom over here, this atom over here, and this atom over here. Okay, now this atom basically belongs to the same unit cell, and we'll basically consider that the matrix elements between this atom and its nearest atoms are given by minus t. Okay, just like our matrix in the last class. This for example is a tridiagonal matrix where we have a main diagonal, we have an upper diagonal, and we have a lower diagonal over here. Similarly, here also let us see the type of coupling. So we will consider that the coupling element or the matrix element between these two atoms is equal to the coupling between these two atoms, which is equal to the coupling between these two atoms, because they are basically equidistant from this atom over here. All these three atoms are equidistant from this atom over here. Okay, and we will assume that this coupling is equal to minus t. Okay, so now how do we write this hk? So this atom A is basically coupled to this atom, and this belongs to the same unit cell. So this factor dm minus dn is basically 0 in this case because the unit cell is the same. Okay, so dm is equal to dn for this unit cell. Okay, so this is equal to zero minus t. Okay, now this is the self term, how this atom A is basically coupled with itself. I will not state the reason that this term is 0 in this case, because earlier we have seen that we have written this term as E0 in our earlier discussion. We have written it as E0. I will not go into detail why this term is exactly 0, but right now just know this, that graphene is actually a semi metal and it does not have a band gap, and this condition is actually this condition comes from the fact that graphene has inversion and time reversal symmetry. We will not go into the detail of these symmetries, but it is required that this term, these diagonal terms in graphene are basically 0. Now this atom A is also coupled with this unit cell over here. So the coupling exists between these two atoms. Okay, so atom A, and this is atom B of this unit cell over here, and this for this atom dm minus dn, so this quantity, which is basically is equal to this vector over here. So we will consider the vector between two lattice points, not between exactly the 8th atom here and the bth atom here. So we'll so if this is the origin, if this is our origin, then dm is basically this vector, because we would consider the vector to the unit cell, and dn is basically this vector over here. So dm minus dn is nothing but this vector, which is minus a2. Actually this is a2, so this vector over here is minus a2. Okay, so let me write it here. A2. So let us actually mark the unit cell. So this unit cell over here is coupled to this unit cell this unit cell, and then this unit cell over here, and this unit cell over here. So let us mark it as 1, 2, 3 and 4, and this is the 0th unit cell, let us say. Okay, so 0 and 0. So this is basically H10. Okay, plus this atom is again coupled to this unit cell. Actually this one is H10 e to the power minus ik dot d1 minus d0, and again for this one, this what I am writing is H20 e to the power minus ik dot d2 minus d0. Okay, so this is coupled to this unit cell is coupled to this over here, and here atom A is basically coupled to atom B. So this is atom B, and this atom A of this unit cell is coupled to atom B over here. Okay, so we have this as 0 minus t e to the power ik dot d2 minus d1. So d2 minus d1 is basically this vector, sorry, this is this vector over here. Remember that this is our unit cell, so this vector is nothing but it is minus a1. So this is the vector a1, so this vector is minus a1 over there, so minus a1, so e to the power minus I k dot a1, and then 0 0. Okay, because why these two terms are 0 0? Because this atom B in this 0th unit cell is not coupled to either atom A here or atom B here, or this atom in this 0th unit cell is not coupled to atom A in the 2nd unit cell or atom B in the 2nd unit cell. Okay, we are considering only the next nearest neighbors or the nearest neighbors. Okay, so now we have other two terms which denote the coupling between this atom with the nearest neighbor. So this atom B, is basically coupled to this atom A, which is in the same cell, and this atom A, which is in the 3rd unit cell, and this atom A, which is in the 4th unit cell. Okay, so let us write the matrix for those two. So we have plus, we have this term H30, then e to the power ik dot d3 minus d1, and d3 minus d1 is precisely a1. So this matrix becomes the coupling between B and A. So 0 0, then minus t e to the power ik dot a1, and 0 over here. Okay, plus we have another term 0 0, and then the coupling between the let me go to the previous page, between this B atom over here and this A atom over here. So this one is precisely minus t e to the power I k dot a2 and 0. So this is basically h 40 e to the power I k dot d4 minus d0. Okay, so we have written down the terms for the coupling between the 0th unit cell, which is this unit cell over here, and these two unit cells. Now this atom B over here, just as I stated, is also coupled to this atom A, which is in the same unit cell. So since the unit cell is the same, this phase factor here becomes 0 because dm is equal to dn, and this basically becomes minus t and 0 over here. Okay, so this entire thing can basically be written as 0 H0 and H0 complex conjugate 0, and as we know that by definition this is required to be Hermitian. Okay, why this is required to be Hermitian? So that the eigenvalues can be real. Okay, and this is precisely nothing but phi 0. So H0 is basically H0 is basically minus t one minus plus e to the power I minus I k dot a1 plus e to the power I k dot a2. Okay, so we have now arrived at the equation where E phi 0 is equal to this matrix times phi 0. So E is precisely then the eigenvalue of this equation over here. So how we find the eigenvalue? We basically write it in this form: determinant of this matrix EH0 H0 star E is equal to 0, which basically means my E square is equal to mod of H0 square. So E is equal to plus minus mod of H0 because E needs to be real. E is an eigen energy, so it needs to be real, and mod of minus t 1 plus e to the power I minus I k dot a1 plus e to the power minus I k dot a2 mod, and so we have basically minus t 1 plus, so let me write this term here, k dot a1, this is basically equal to kx kx I plus ky j, where I and j are the unit vectors along the x and y directions, and a1 is nothing but 3 by 2 a0 I plus root 3 by 2 a0 j. Okay, so this is 3 by 2 kx a0 plus root 3 by 2 ky a0. Similarly, k dot a2 is equal to 3 by 2 kx a0 minus root 3 by 2 ky a0. Okay, so we can write this as e to the power minus I kx a0, or we write this, we just basically cut this 3 by 2 and write it as a and b, so that it's actually more easy to manage. A and b, where a is basically 3 by 2 a0 and b is basically root 3 by 2 a0. And just remember that a0 is basically our unit vector. So a0 is this distance over here. Let me just, in case you don't remember, let me remind you, this distance is a0. Okay. So kxa, we put a second bracket over here, e to the power I kyb plus e to the power minus I kyb mod, and this is equal to twice the cos of this argument over here. So minus t 1 plus e to the power I kxa 2 cos kyb, and this is equal to minus t minus 2t cos kxa cos kyb minus 2t sin kxa sin kyb, and we have a minus t, an extra, so minus t over here, and the mod of the entire thing. So this is nothing but so we have a plus minus over here. So here, by squaring this term, we get 4 cos kx cos square kxa cos square kyb, and then when this is added with this term, this sine square over here and this cos square over here becomes 1, and which we are left with 4 cos square kyb whole to the power half. Okay. So this is our basically expression for eigenenergy. E is equal to plus minus t root over 1 plus 4 cos kxa cos kyb plus 4 cos square kyb whole to the power half, and we note that there are 2 bands, one for this positive sign and one for this negative sign, and these bands basically run in opposite direction. Okay, so one of them is basically the conduction band and other is basically the valence band, and to see whether this graphene basically has a band gap or not according to this Hamiltonian. It's not difficult to find out. We just need to understand that whether there are any points within the Brougham zone or Brillouin zone for which this expression basically becomes 0. Okay, if this expression basically becomes 0, then it is well understood that graphene does not have a band gap. Okay, both the bands start from 0 and 0 is their point of intersection. Okay, so how to understand? So let me just if graphene doesn't have a band gap, then this H0, so we had to return it as, let me just go back. Yeah, so this H0 must be equal to 0 for some value, and mod of H0 equal to 0 basically means that the entire thing H0 must also be 0. So this term should also be 0 inside this mod sign. Okay, so then H0 should be equal to 0 for some value of k, and let us see if that is the case. H0 equal to 0, this basically implies that 1 plus e to the power I kxa cos kyb, we had a 2 here, this should be equal to 0, which basically means that 2 e to the power I kxa cos kyb should be equal to minus 1. Now note that this part has both real and imaginary terms, because this term has both real and imaginary term, but on the right hand side the term is completely real, so this term must also be completely real, and the only value of kxa, or the only value of this argument for which this entire term is real, is basically kxa equal to 0. Okay, so this implies that kxa should be equal to 0, or it can be equal to n pi. I'll write it as n pi, where n starts from 0. Okay. Now when it comes to Brougham zone, because Brougham zone, the first Brougham zone has both the positive and negative kx axis, we can add another set of points here, which is kxa equals to plus minus pi, sorry, kxa equal to minus pi, because plus pi we have already written, and kyb is equal to plus minus pi by 3. So in total we have 6 points. So let us just look at these 6 points. So this point over here, this is equal to pi by a pi by 3b, which is basically 1 point from this set. Okay, so this contains plus minus here, so this is equivalent to 2 points. Okay, and then the second point from this set basically is this point over here. Okay, similarly for this set over here, 1 point is given by this, and the second point, that is minus 2 pi by 3, kyb equal to minus 2 pi by 3, this point is basically given by this point over here. And similarly from the third set, 1 point is basically this point, and the second point is this point over here. Okay, so we have 6 points in the Brougham zone, and the band gap is precisely 0 at each of these 6 points. Okay, so the band gap is basically 0 at all these 6 points. Now note that these 6 points are basically shared by each of these 6 points are basically shared by 3 unit cells. For example, there is a hexagonal cell like this. This is a reciprocal lattice. There is one hexagonal cell like this over here, and there is another hexagonal cell like this over here. So this point is in total shared by 3 different hexagonal cells. One is this cell, one is this cell, and one is this cell. So 1/3 of this point exactly belongs inside the first Brougham zone. Okay, similarly 1/3 of each of these points belong inside the first Brougham zone. So in total there are 2 points which basically belong to the first Brougham zone. Now note an interesting thing which might not be obvious at first is that, just as I stated, that in total there are 2 points within the first Brougham zone, 2 lattice points. Lattice points means the reciprocal lattice points in the first Brougham zone, for which the band gap is exactly 0. Now note that these 2 points are actually not equivalent. Okay, and you may ask the question that why these two are not equivalent. The exact same reason why this atom and this atom here are not equivalent. Okay, so I would not say that there are 2 lattice points inside the Brougham zone for which the band gap is 0, but let me reframe the statement, because one unit cell only contains one lattice point. So a better statement to say would be that there are 2 inequivalent K points inside the first Brougham zone for which the band gap is 0. Okay, now these 2 K points are not the same, or these 2 K points are not equivalent, and why they are not equivalent is exactly the same reason that this atom here and this atom here are not equivalent. Okay, because they do not see the same crystal structure. So that is why these 2 atoms basically constitute one unit cell, because this atom and this atom are not equivalent atoms. Okay, similarly this point and this point are not equivalent points, and this basically constitute the unit cell in the reciprocal space. Okay, similarly we have something like this here and something like this unit cell here, and all these K points shown in black are actually equivalent to each other, and all these K points shown in white, that is this point, and this point, are equivalent to each other, and those which are shown in black, this point, and this point are equivalent to each other. Okay, so I'll not go into too much detail regarding this thing, but I hope that I have given you a sense of how things are. So this will basically mean that there are 2 inequivalent K points, or 2 valleys, over which the band gap reduces to 0. Now let us discuss about graphene nanotubes. Of course you have heard about nanowires and nanoflakes, but nanotubes you might not have heard. And graphene nanotube is basically the same as any other nanotube. So once you understand how to analyze these structures, or what these structures are, you would be able to analyze any kinds of nanotubes. The only thing is that the method is basically the same, but the specifics might be a little bit different. Okay, so these 2 structures basically shows a sheet of graphene. These 2 structures are basically the same. Now what is nanowire? Nanowire is basically a tube like structure, not a tube, but a cylindrical structure or a square structure whose properties resemble that of the one-dimensional electronic states or one-dimensional electronic wave function. Okay, now this region in a nanowire is basically solid, so this region basically contains atoms. Okay, now if I roll a 2D sheet, So let us say graphene. Graphene is a 2D material. If I roll a 2D sheet, okay, I would get something which is hollow inside. Okay, and the structure that is formed is known as nanotube. So I do have a small file over here which demonstrates how nanotubes are basically formed. So let me just open it up. It's not my creation, but I took it from the internet. Now this short video basically demonstrates how nanotubes are formed and how they are constructed. So we have a 2D layer of graphene or any other 2D material, and they are basically wrapped around to form a cylindrical structure. Now if you wrap a 2D material, it would form a surface, it would form the surface of a cylinder with hollow structure inside. Okay, a cylindrical hollow structure is formed when you wrap this 2D layer, and that is what is known as nanotube. Now as you see that the same graphene sheet can actually be rolled along the horizontal direction or along the vertical direction, and they basically give rise to different structures. So let me demonstrate. First note that this line here, so this line or the nature of how this surface varies here is different from how the surface varies here. Okay, I again repeat that the nature of variation here along this line is different from how it varies over here. So here it is kind of zigzag. Okay, it's a kind of serrated, and somewhere here it basically resembles an armchair. So now what will happen if I do a horizontal roll, or if I roll it along the horizontal direction? So what is meant by the horizontal direction is that I have this axis, and this axis which is horizontal, and I roll this nanosheet around this axis. So this point becomes joined with this point joins with this point over here, this point joins with this point joins with this point over here, and so on, and this line is left unaltered. Okay, so what I get if I roll it along a horizontal axis is basically this structure over here, and this structure, in this structure we see that this zigzag shape remains unaltered, and this is known as zigzag nanotube. On the other hand, if I roll this same nanosheet along a vertical axis like this, okay, so this is the axis of the cylinder that forms when I roll this nanosheet into a hollow cylindrical structure. So what happens then is that this point becomes same as this point joins with this point, and so on, and this surface remains unaltered, and then what I get is this kind of structure where I can still see this surface, and this kind of nanotube is known as armchair nanotube, because this line over here, this open line over here, resembles that of an armchair. This nanotube here is known as zigzag nanotube because this open line over here resembles a zigzag structure. Okay, similarly I can actually roll it along any axis. I can roll it along this arbitrary axis and get another cylindrical hollow nanotube. This kind of nanotubes are known as chiral nanotubes. Okay, I basically in that case I get this kind of structure, and these chiral nanotubes might have many orientations. For example, I may roll this nanotube along this axis. I may roll it along this, not this, this is the horizontal. I may roll it along this axis, and I may roll it along this axis. So there are many kind of configuration that can occur for a chiral nanotube. Okay, so both of these nanotubes have not both of these, but all these nanotubes basically have different sets of properties, and since now we have joined, or we have rolled up this nanosheet, we need to basically rely on periodic boundary condition to analyze this kind of structures. Now note that when we roll up this graphene nanosheet into a nanotube, the Brougham zone basically remains unaltered. Okay, because the Brougham zone is basically the set of all k vectors that reside within an energy band or the range of k vectors. Now we can get the range of k vectors or available or let us say possible, not possible, but the range of k vectors within an energy band from the Brougham zone or Brillouin zone. However, the actual values of k, that has to be determined from boundary conditions. Okay, so this is the same as saying that if we have an infinite potential well like this, and this potential well consists of 5 atoms with interatomic distance a, then the range of k values can extend from 0 to pi by a, or from minus pi by 2a to pi by 2a. However, the exact value of the k vectors has to be determined from the boundary conditions that the wave function at this point and at this point precisely reduces to 0. Okay, so this is the range of k vectors that we can get, but within this range, because my number of points is finite, there would be some specific values of k or allowed values of k vectors for which the wave function is 0 at this point and at this point over here. So same is the case in these nanotubes. Okay, now let us assume that I roll my nano sheet along an arbitrary axis. So this is the axis of the cylinder. So let us say that this is the axis of the cylinder along which I roll my nano sheet. It's difficult to draw a straight line over here, but one of the axes is already given, which is this axis over here. Okay, so let us say that this is my axis over which I roll my cylinder, so over which I roll my nano sheet. So whenever I roll my nano sheet, this axis of the cylinder constitutes of this axis over here. Okay, and let us say that I define this vector c to be m a1 plus n a2, where a1 and a2 are basically the lattice translation vectors of graphene, and if you don't remember, a1 is equal to a 3 by 2 a0i plus root 3 by 2 a0j, where I and j are the unit vectors along the x and y direction, and a2 is basically equal to 3 by 2 a0i plus root 3 by 2 a0j. Okay, now you have to remember, sorry, this is not actually the axis of the cylinder along which it should be rolled. Let me just correct myself. This is actually the axis of the cylinder, which, or the axis that forms on rolling up this graphene sheet. Okay, so if I roll up this graphene sheet along a chiral direction, then this is basically the axis of my hollow cylinder, and this is the circumferential vector along which I am rolling the graphene sheet. Okay, now when I roll the graphene sheet, I have to connect two equivalent points. For example, this is one unit cell of graphene, so it is evident that this point and this point, they are not basically equivalent points. Okay, these two are different, and this is what forms the unit cell in graphene. So now let us say that when I roll it up, this point and let us say that this point and this point can connect. On the other hand, I would not be able to connect this point and this point over here. If I connect this point and this point, then it would form an unstable arrangement, because these 2 points are not really same. Okay, this point and this point are not really equivalent points, so I cannot connect these two structure. If I connect these 2 points, then it would form an unstable structure. Okay, the crystal structure would basically get damaged, and you can understand why, that it would basically form a deformity within the crystal structure. Okay, so when I roll it up, I have to connect, let us say, I can connect this point and this point, or this point and this point, depending on the depending on what is the chiral vector along which I am basically forming the nanosheet. Now I have to connect 2 equivalent points, and let us say that I connect this point over here and this point over here, and so these 2 are equivalent points. Okay, so this is my circumferential vector C equal to m a1 plus n a2, and when I connect this point and this point on forming a cylinder, these 2 points become equivalent, and so the wave function, when it completes an entire loop around this cylinder, the value of the wave function or the phase of the wave function along at this point and this point should basically be the same. Okay, so which is to say that this quantity C dot K or K dot C, whatever you call it, this should be equal to 2 pi times an integer, let us call this integer v, for any given vector k. Okay, I repeat again that when I basically wrap up this nanosheet, I am basically connecting this point and this point. Okay, this is the part of the nanosheet which I am cutting and wrapping up. Okay, so this point and this point is connected, not only this point and this point, but the other points are also connected. So whenever, and this is the vector along which I am wrapping my carbon nanosheet. So whenever I wrap my carbon nanosheet, because this point and this point connects up, so whenever the wave function makes an entire loop around this nanosheet, the value should be the same. So the phase at this point and at this point should basically be the same. Okay, otherwise that wave function cannot exist within the nanosheet. So this basically means that the circumferential vector C dot the wave vector k should be equal to 2 pi v, where v is an integer. Okay, so v is an integer. Now I just put these values over here. So this is m a1, and a1 is basically given by this vector over here. So let me write the full form: 3 by 2 a0 I cap plus root 3 by 2 a0 j cap dot kx I cap plus ky j cap plus in 3 by 2 a0 I cap plus minus root 3 by 2 a0 j cap dot kx I cap plus ky j cap. This is equal to 2 pi times an integer. Okay, so what I get at the end is m plus n kx into 3 by 2 a0 plus m minus n root 3 by 2 a0 m minus n ky. This is equal to 2 pi times an integer. So this is a periodic boundary condition basically. Okay, now what does this equation over here give us in the kx ky plane? So we have kx over here, we have ky over here, which are variables, and then this part is a constant because m and n it depends on how this nanoshift is basically wrapped up or how this nanotube is basically formed. So this part is a constant over here, this part is a constant over here, okay, and then we have this kx and ky, which are basically variables, and then we have this thing over here. So this is equivalent to the equation, let us say p kx plus q ky equal to r. So what is this equation? This equation is that of a straight line, okay, and because v here is not confined to any particular value of integer, and v can be any integer 1 2 3 4 etc. So therefore we get a straight line in the kx ky plane for each values of v, okay. So let us say that this is our Brougham zone or Lewin zone for graphene, and for each values of v I get a straight line like this, okay. So these straight lines are kind of like the subbands for this for this nanotube. Just like in a 1D structure we have subbands, in a 2D structure we have subbands. Similarly, in this nanotube also, this line over here, this basically denotes subbands in the kx ky plane, okay, each for a given value of v, okay. Now whether for a given value of this parameter v a subband will display energy gap or not, that would depend on whether this straight line passes through any of these 6 corners. So these are the points at which the band gap is 0, just as we discussed earlier. These are the 6 points at which the band gap is 0, and if any of these lines corresponding to a given value of v, if any of these lines corresponding to a given value of v happens to pass through any of these corner points, then that particular subband would not display any energy gap, okay, because these corner points are precisely the points at which the energy gap is 0, okay. For example, in this case, this straight line over here, corresponds to a subband which does not display an energy gap because it basically passes through these corner points over here, okay. So for this particular subband, or for this particular line corresponding to a subband, the energy gap is basically 0, okay. So I hope it is somewhat clear to you. This is slightly complicated, so you have to do a bit of reading, and I believe that to understand this you have to put some effort, you have to think about it. So let it sink in, and we will discuss about zigzag and armchair carbon nanotube in the next class. Thank you everyone.